Hello. This presentation, entitled The Measurement Problem 3, Interpretation or Existence of a New Non-Unitary Process, is our third in our series of educational videos on the measurement problem. I'm Dr. Michael Steiner, and I work with Dr. Ronald Rendell on the investigation of the measurement problem. There are 6 sets of videos which compose the measurement problem lecture series. These lectures are complementary to our book, The Quantum Measurement Problem. In this, our third video, Interpretation versus Existence of a New Non-Unitary Process, you'll understand why the measurement problem implies that a real physical non-unitary process exists and learn to fully appreciate the significance of this problem. This lecture is presented in 2 parts, 1 and 2. Before we begin the main part of this presentation, we'll present a brief review. In our past presentation, we emphasized that unitary evolution is a reversible operation. The wave function in the future can be determined from knowledge of the past wave function. Due to these considerations, entropy is unchanged under unitary evolution. The information content of the wave function is the same throughout time. That is, no new information is created and no old information is destroyed. We now briefly review our prior modeling of a Schrödinger cat. Consider the wave function evolution for a photon that goes through the beam splitter in the superposition minus I 1b 0c plus 0b 1c, all normalized by the square root of 2. The first term leads to the state minus 1b 0c, red 1 of mirror 1, and black 2 for mirror 2. This first term, for which the photon enters the beam splitter and exits through port B, leads to the state for which mirror 1 at the output of B experiences a recoil, while mirror 2 does not experience any recoil. This can also be seen by the dotted lines that encompass the red mirror on the left and the black mirror on the right. The second term leads to the state minus I 0b 1c, black 1 for mirror 1 and red 2 for mirror 2. And this can be seen diagrammatically by the other set of dotted lines in the diagram on the bottom right. By linearity of unitary evolution, the state minus I 1b 0c plus 0b 1c over the square root of 2 evolves to minus 1b 0c red 1 black 2 plus I 0b 1c black 1 red 2, all divided by the square root of 2. And this is an example of an entangled state. One can continue further and add more mirrors. The unitarily evolved state of mirrors just continues to grow. The state evolution has 2 terms. In our first term, for which the photon exits the beam splitter at port B, we have red terms R1, R3, R5, R7, R9, corresponding to the respective odd mirrors M1, M3, M5, M7, M9, which indicates that these mirrors have experienced a recoil due to the photon interaction. And in this same term, we also have appended the black states B2, B4 up to B10 for the respective even mirrors M2, M4 up to M10 on the right side of the interferometer, because these even mirrors do not recoil. In the second term, where the photon exits the beam splitter at C, we have the opposite occurring. So one can see that the entangled state is encompassing more and more interactions, but yet notice that there are still only 2 terms present. Suppose we carry this analogy further, whereby a photon enters the beam splitter, as shown in the diagram, and either exits above via port B, or is deflected by the beam splitter via port C, for which it heads directly to someone's eye. Let us assume that the eye has M neurons, and that the initial unexcited state of the neurons is denoted by the superscript 0. In the case that the photon exits the beam splitter from port B, the neurons in this case can be assumed to stay in the same initial state of having not been excited, whereas for the case when the photon exits the beam splitter at C and heads toward the eye, the neurons will be excited, and we will denote their excited state by the superscript 1. Now suppose that a photon enters and exits the beam splitter in a superposition of the output ports B and C. In other words, we have the state 1b 0c plus I 0b 1c normalized by the square root of 2. Then one can see that the unitarily evolved state becomes 1b 0c, and then we have the neurons n1 through nm all with the superscript 0 plus the term I 0b 1c, and then we have all of our neurons n1 through n sub m with the superscript 1, and all of this is normalized by the square root of 2. Well, when one looks at this state, the I would be predicted to be in a superposition of seeing and not seeing the photon. But then we said, why stop at the I? Consider unitarily modeling the neurons in the brain that are excited when one sees the light. Well, then one ultimately produces a superposition of two of you, one that saw the photon and one that did not. And if one could attach various emotions to the different cases, for example, when one sees the light, one could be happy, and one doesn't see the light, one is sad. Then one produces a superposition of emotional states. So we get the rather extreme prediction under unitary evolution of the same man in a superposition of two emotional states, the happy man that saw the light and the unhappy man that did not. But in fact, we know by our own experience that this does not appear to be happening. So somewhere the unitary prediction appears to be going wrong. Now, one of the important characteristics of the quantum state that is predicted under unitary evolution is the characteristic of entanglement. It was proven by Bell for the case of two particles that entangled superpositions have properties that cannot be explained by any initial state lambda that is a classical state or tensor product state AB. We will be using the characteristics of entanglement when we further analyze the measurement problem in more depth. The prior presentation showed a difference in the state that is expected under unitary evolution when compared with the case of measurement. In the case of unitary evolution, we expect a superposition state, whilst in the case of measurement, we expect a product state. But the arguments that were given did not rigorously establish that there was necessarily a real problem. That is, how do we know if interactions other than a mirror are used, the problem doesn't just go away? Or if the problem goes away when the number of particles and interactions composing the detector becomes macroscopically large. In this presentation, we will directly address these issues, as we will rigorously establish the existence of a non-unitary process in nature. In the past presentation, we used a model of the photon interacting with a mirror in order to illustrate the measurement problem. However, one might argue that this is a heuristical model, and a rigorous treatment would require a Hamiltonian model that can be completely treated with quantum mechanics. So in this presentation, we will use a detailed model of the detector, and with this model, it will be demonstrated quantitatively how the measurement problem can be reduced by an appropriate positive operator valued measurement, which is POVM, to a problem of 2-qubit entanglement. And it will also be demonstrated what the new predictions of the POVM are for the cases of unitary evolution and under measurement, and that these predictions are independent of the number of particles that interact with the incoming photon, and independent of the Hamiltonian of the detector. That is, any number of particles that compose the detector and any types of interactions can be utilized within the detector, and we will still obtain the same results. Following these arguments, the viewer will appreciate that there is a measurement problem for any given configuration of particles that form the detector. The argument often put forward that somehow the measurement problem goes away for macroscopically large detectors is conclusively invalidated. Similarly, the argument that particular unitary interactions cause measurement is also invalidated. And this will lead to the phrase, to the extent that there is entanglement, there is no measurement. Here's our previous heuristical model, whereby we had photons going through beam splitters and then impinging on mirrors, causing them to recoil. Now, we assumed it is impossible to have direct interaction terms between mirror 1 and 2 as long as d, the distance between the mirrors, is greater than c, the speed of light, t sub m, which is the recoil time of the mirrors, plus p, where p is the photon wave packet extent. And this is the case even in rigorous modeling, which is what we're going to begin to do. you still have, as long as the two detectors are physically separated by a distance d, you still cannot have direct interaction terms as long as this equation d greater than ctm plus p is met. A significant issue remaining is whether the unitarily predicted superposition can be asymptotically associated with a product state, in other words, not an entangled state, when the detectors have a macroscopic number of particles n. To rigorously answer this question, we will replace the mirrors in the prior presentation by a photon in the detector described as a closed system via a Hamiltonian. We will use a spin system to represent the detector, although any system can be used. We will compare the cases whereby the final state is a tensor product state expected under measurement versus an entangled state predicted under unitary evolution. Our detailed particle detector model is shown here. We have a photon with Hamiltonian HF, which is composed of two field modes as before, B and C. Detector 1 is composed of N1 particles and has a self-Hamiltonian H1. Detector 2 is composed of N2 particles and has a self-Hamiltonian H2. And we're going to consider the general class of Hamiltonians, which is H equals HF, so the first part of this Hamiltonian is the field. And the second and third are the detector 1 is the second, and the third part of the Hamiltonian is the detector 2. So this first term, HF, is the field. The second term is the H1, and the third term is the self-Hamiltonian of H2. And then to that we add the interaction. And the interaction is between the field and, for the first one, HF1. So it's the interaction between photon mode B and detector 1. And HF2 is the interaction between photon mode C and detector 2. Now you've noticed we don't have any direct interaction, for example, between detector 1 and detector 2. Now our detector model is the Hamiltonian HF for the field plus H1 detector 1, H2 detector 2 plus the interaction H int. Now here we're going to go into more detail that requires a background in quantum mechanics. And so if you're not that familiar with quantum mechanics, then you should just listen here and try and absorb the main points. On the other hand, if you are fluent in quantum mechanics, then by all means go through all the details here. We'll define sigma plus as a raising operator and sigma minus as a lowering operator on a two-state system. I is the identity, Ix, Iy, and Iz are related to Pauli spin matrices. And we'll consider a two-spin Heisenberg model for each detector. Now, in this case, the Hamiltonian used is the same for both detectors. And so each detector has two particles or two spins in it. And the first term is just Iz, tensor I, and the second I2 tensor Iz, meaning, so this is the self-Hamiltonian of the two spins. And then we have three interaction terms, Ix tensor Ix, Iy tensor Iy, and Iz tensor Iz, all weighted by these J couplings. Our field is omega A prime AB prime AB tensor I plus omega I2 tensor AC prime AC. So these are boson operators. And so essentially we can have arbitrary numbers of photons in the B mode or C mode with this field Hamiltonian. Now one might ask why we've chosen this particular model. In fact, this model is used by those who conduct nuclear magnetic resonance experiments. And in fact, there's a whole area of quantum computing that uses nuclear magnetic resonance techniques. So it's possible, actually, that these types of models that we're doing for detectors could actually be tested using NMR quantum computing. But as we'll see, our results are independent of the detector model. So one does not require a NMR detector model. One can use any arbitrary Hamiltonian that represents the detector. In this view graph, we will present the interaction Hamiltonian between the field and detectors. The Hilbert space, the overall Hilbert space, is 64-dimensional, which can be broken down into 4 by 4 by 4 dimensions. The first four dimensions represent the field, the second four dimensions the detector 1, and the third four dimensions represent detector 2. Now, the first four field dimensions can be further decomposed into 2x2s, where the first two is the B mode of the field and the second two is the C mode of the field. Now, the second four of the 4x4x4 64-dimensional space represents the particles in detector 1, and since we have two particles, this likewise as the field can be further decomposed into a 2x2, whereby the first particle is in the first two-dimensional space, and the second particle of detector 1 is in the second tensor Hilbert space. Finally, detector 2 is likewise in a four-dimensional Hilbert space, as it also has two particles, each of spin 1/2. For our interactions HF1 and HF2, we will have a field mode interact with only the first particle of the respective detector. So one can see our HF1 is defined as AB, which is the annihilation operator for the field mode B. And then we have tensor I, which means for the C mode, it doesn't do anything, it's just an identity. Tensor the raising operator for the first particle in detector 1, and tensor I for the remainder. And plus, we add the complex conjugate of that, which is the creation operator on field mode B, meaning we create a photon, and eventually tensor sigma minus on the first particle of detector 1, meaning we lower it, or the atom or the spin, we flip the spin. Now, HF2 is simply the same type of thing, except where you're going to use the second part of the Hilbert space for the field, which is mode C. And we will also use the first particle in the detector 2 Hilbert space, so we have sigma plus there. And we also add to that the complex conjugate, where we create a photon in the C mode, tensor a lowering operator on the first particle of detector 2. And so we have these two interactions, HF1 and HF2, and we add them, and that's our overall interaction. Now we're going to define the initial state of the field as an arbitrary size 0f, and let the initial state of detector 1 be size 0, and the initial state of detector 2 be size 0 for 2. And the initial state, so overall, is a tensor product size 0f, size 0, 1, tensor size 0 for detector 2. Now we are going to present our assumptions for the case of measurement. Let us assume that when we input size 0 for the field, which is a photon in B but not in C, we find for the case of detection registered at 1 that the state of the field detectors is a product state. Psi field is given by no photons in the field, tensor a final state, psi 1 of the detector, tensor psi 0, the initial state, so of detector 2. So here it is assumed that detector 2 just remains in the same state as it started. So psi 1 is the state of the particles composing the detector to detector 1 after a detection is made. Now we're assuming that it is assumed psi 1, the final state of your detector 1, is orthogonal to the initial state, psi 0 of detector 1. When we input psi 0 for which a photon is at C, we find likewise that for the case of detection registered at detector 2, that the state of the field detectors is again a product state with similar characteristics as before. Now, when we input an arbitrary psi field and neither detector registers a photon, so this is a possibility, the state of the field detectors is assumed to remain in its ready state. So we have for those cases some final psi field, and both detector 1 and detector 2 remain in its initial ready state. Now, the viewer might have noticed that the assumptions here require that there be a single final detector state, which would be, for example, psi 1 for detector 1 or psi 1 for detector 2. And this is fine for certain cases of interest. For example, for now we will assume a detection occurs when only the first qubit of the 2-qubit detector is excited. In this case, there is a single quantum state that represents this detection state. But one might ask if this can be generalized so that a detection occurs when either qubit 1 or qubit 2 composing the detector is excited, but not both. You might ask, why not both? Well, we can't have both excited, as this would violate conservation of energy requirements. So the question is whether there is a quantum state corresponding to when either qubit 1 or qubit 2 is excited, but not both. Since the detector state in this case is not either the case of single qubit 1 excited, nor the state of qubit 2 excited, one might initially consider here a detector state which is a superposition state of qubit 1 excited, tensor qubit 2 ground, plus qubit 1 ground, qubit 2 excited. Assumptions for the case of unitary evolution are that if we input into the A port of the beam splitter, then we generate from the remaining 2 ports a superposition state, which is minus I, 1B, 0C, plus 0B, 1C, all normalized by the constant square root of 2. Now the field detector 1, detector 2, so everything, the field and all particles, will evolve under unitary evolution, and this is simply given by the psi final state equal to the U, which is just e to the minus I tau h, tau being the time of evolution, times the initial state, which is here the superposition state for the field, and tensor the 2 initial states, psi 0, which is a state of 2 particles for detector 1, and psi 0 for detector 2, which is also a state of the 2 particles for detector 2. And after evolution, the final state can be further characterized via 2 separate measurements on the detectors. After either the case of unitary evolution or the case where the detectors measure, the final state can be further characterized via 2 separate measurements on the detectors. So here we show a measurement on field B, detector 1, and here we show a measurement on field C, detector 2. These measurements are actually a generalization of Bell measurements. Note the figure on the right. We see that there's 2 measurements being made on these detectors. And this, in the case of Bell measurements, it was just a single photon and a Hilbert space of 2 dimensions for each detector. But this is a generalization because the detectors can be many particles. And so we'll assign a +1 if the detection is made and a -1 if there is no detection. Now at this stage it may be worthwhile reviewing Bell's inequality. Here we have on the bottom a figure of a Bell apparatus. And what we'll have is a source that will output 2 photons, one going toward A and one going toward B. And the one that goes toward A impinges on a beam splitter, which if it's transmitted, it registers a 1, and if it's reflected, it registers a -1. And this beam splitter has a parameter of theta A. And similarly, if for the photon going toward the right, we have a beam splitter with variable parameter theta B. And the photon that is transmitted registers a 1, and that is when it's reflected, it's -1. And it turns out, if we let rho AB be the average, if we do this many times of AB, given the parameters theta A and theta B, that the following is derived for any classical product states of the initial state. So we have the correlation AB minus AB prime plus A prime B plus A prime B prime is less than or equal to 2. But quantum mechanics, if you have an entangled input state, predicts the cosine 2A minus B, which yields a much larger value, 2 square roots of 2. And this is actually very relevant also, in addition for non-locality, it also is very much relevant for the case of measurement. Relevant in the sense that suppose that we demand that when we observe a definite state at A, such as horizontal polarization, and a definite state at B, such as vertical, that this corresponds to a tensor product state of HV emitted at the source. If this is the case, then one must satisfy the inequality. That is, we need to be less than or equal to 2. Similarly, for the case of measurement, we require that the outcomes of experiments be describable by classical tensor product states. Hence, Bell's inequality in this sense is not only important for non-locality, but also serves as a critical tool for analysis of the measurement problem. Bell's inequality was designed around making measurements on the polarization of a photon, which is a two-dimensional Hilbert space. On the other hand, our detector may consist of a large number of particles. So we need to generalize the original Bell measurement to a measurement on a detector, and as well on the photon field in the vicinity of the detector. We will assume the beam splitter is a polarizing beam splitter, and the degree of superposition at B and C can be controlled. The probability equals A that the photon is found at B, and 1 minus A that it is found at C. So we'll consider the final state after unitary evolution to be psi final equals the unitary evolution U, and we have the initial state of the field square root of A 1B 0C minus square root of 1 minus A 0B 1C, and we have tensor the two initial states of the detectors. In order to generalize our Bell measurement, we're going to take a slight diversion and explain a Schmidt decomposition. Let psi be a pure state of a composite system AB. Then there exist orthonormal states E sub I in A and F sub I in B, whereby one can write the pure state psi equal to square root of V sub I, E sub I tensor F sub I. So V sub I are actually going to be real and non-negative, and the sum of these V sub i's is equal to 1. For example, if we have an entangled state, square root of A 1, 0 plus square root of 1 minus A 0, 1 is a Schmidt decomposition with Schmidt coefficients square root of V sub I. Furthermore, suppose psi and phi are two pure states of AB with the same Schmidt coefficients. Then there exist unitary local transformations x and y acting on AB respectively such that psi equals x tensor y phi. Now, one of the nice properties of these Schmidt decomposition is that it allows one to visualize geometrically what quantum states look like. Now the first thing we have here are product states. We have in system 1 a vector E1 and a system 2 described by vector F1. And so psi for the composite system of system 1 and system 2, a composite system being more than one particle, we have psi equals E1 tensor F1. Now another possible pair of product states are shown here. For system 1 we have E2, and system 2 we have F2. Here we have psi equals E2 tensor F2. Well, what about if we have a superposition state which can occur in quantum mechanics? Here we are shown system 1 can have one of two states, E1 or E2, and they are perpendicular or orthogonal. And system 2, F1 and F2. Now the red E1 on system 1 is going to be paired with F1 on system 2. They're both red. And E2 in the green is paired with F2 in the green in system 2. This means that if one encountered or measured E1, for example, in system 1, it would always be found to system 2 to be in F1. And also, if system 1 was found in E2, then system 2 would be found in F2. Here we have a superposition state which has E1 and F1 weighted by the square root of A, and E2 and F2 for system 1 and 2 weighted by square root of 1 minus A. And this is a perfectly good Schmidt decomposition, and our Schmidt coefficients being square root of A and square root of 1 minus A. An example of this Schmidt decomposition is to consider the initial photon entanglement that we have after a photon goes through a beam splitter. For example, suppose psi equals square root of A 1, 0 minus square root of 1 minus A 0, 1. And these are for the mode BC, modes BC coming out of the beam splitter. Well, that can be rewritten as square root of A E1B F1C plus the square root of 1 minus A E2B F2C, where E1 of B is just 1, the same as the 1, and F1 is defined to be the 0 of C. But E2 of B will be defined to be minus the 0 state of B, and F2 is just the 1 of C. Well, as we're nearing the end of our presentation of Part 1, we thought we'd take a break and head up to the Army-Navy game. And don't forget to pick up Part 2 after the Army-Navy game intermission. Here we are, up in Philadelphia, at the Army-Navy game. Okay, we made it. Great, it's a nice day. We have nice seats and view of the game. What could be better than this? Well, what a coincidence. We see that sitting adjacent to us on our right are the Army Senior Executive Service SES managers, who we understand are very interested in quantum information. Oh, and wait, we see on our left are the Navy Senior Executive Service managers. What a great opportunity! As we were so hoping that they will fund our research, and we just so all happen to be here together, we'll give them a brief tutorial on our work. Okay, Army SES managers, repeat after me. To the extent there is entanglement, there is no measurement.
To the extent there is entanglement, there is no measurement.
Well, not great, but at least that's a start. Maybe the Navy can do better. Navy managers next.
To the extent that there is entanglement, there is next.
Did I hear something about Star Trek? Okay, again, Army Research Laboratory. Let's see if you can do that better in sync. To the extent that there is entanglement, there is no measurement.
To the extent that there is entanglement, there is no measurement.
Well, not bad, but try and make it a bit louder next time. Okay, Naval Research Laboratory.
To the extent that there is entanglement, there is no measurement.
Measurement? I don't really know. Oh, where's my masseuse?
Well, I don't know, Navy. Last chance, make it loud. Sports fans, feel free to give an applause to whoever you think understands the measurement problem better. Army, you're up.
To the extent that there is entanglement, sir, there is no measurement. Sir.
Wow, very good, Army. Okay, last chance, Navy. Who knows where that came from? Okay, it looks like our crowd has picked a clear winner. It's the Army.